Welcome back to the Poor Pro's Almanac. This is Andy, and today we're joined by Dr. Jim Ippolito, a renowned expert in soil health and fertility from Ohio State University. We're talking about the innovative use of soil bacteria to enhance nutrient availability. Our discussion challenges traditional farming practices and unveils how leveraging natural soil biology can revolutionize sustainable agriculture, potentially reducing reliance on external fertilizers. We dive into the fascinating connections between soil microorganisms and human biology, drawing parallels that underscore the profound interconnectedness of all life forms. Jim has a visionary approach using bacteria to reshape agriculture and addresses the economic and practical challenges faced by producers transitioning to sustainable methods. Lastly, we explore the potential and challenges of biochar and biosolids in agriculture, and how integrated agroecosystem management or agroecology can pave the way for eco-friendly farming. So please take a listen, let us know what you think, and if you haven't yet, please give us a review on iTunes or Spotify, wherever you're listening to this, because it does help us rank higher in searches. With that said, let's dive in. Jim, thanks so much for joining us. I came across a bunch of your papers, found what you're doing really interesting. I'm really excited to have you on. Please tell us a little bit about yourself.
Yeah, Andy, thanks for having me. I really appreciate it. So my name is Jim Ippolito. Right now, I'm currently a professor of soil health and fertility at The Ohio State University. I spent 25 years of my life at Colorado State University in the soil science realm, and somewhere in between, I spent about 10 years of my life working as a soil scientist for the USDA Agricultural Research Service in Idaho.
Awesome. So yeah, it's nice to see academics that actually go out and then do the work, because sometimes that doesn't happen, and you end up with kind of like a strange perspective on how to fix stuff, which I think gives you some really good insight.
Well, you're right, because first of all, I really love what I do. And I like taking basic research and applying it to solve a problem. And I've done so for my whole career.
Yeah, and like I said, your name's been on quite a bit of interesting research, some of which I think is really cool, like this idea of like utilizing bacteria in the soil, which is, I think, something that you see a lot in like the alternative hippie, homesteader, permaculture type spaces. But you're putting some like academic focus on that and like how our understanding of bacteria can help us be better about how we manage the soil, and particularly with like phosphorus and things like that. So I don't know if you could speak a little bit about that.
Yeah, I can. That work is really exciting. And you're right. It's sort of, that one-off hippie-ish type of research that you mentioned, Andy. I wouldn't say it's really hippie, because it's real.
Well, it's like the nature's fixing itself kind of stuff. No, I'm not against it. I just think when we talk about it, it's like, the hard science of the farmer who's like, well, we need to add these things to the soil, phosphorus, nitrogen, and so on. And then like the soil biology as a component of how we access those things, I think is a very modern understanding that I think has been better understood longer in those spaces. Is that better? More clear?
Yeah, that's more clear. I think about the type of work. So let me take a step back. So first of all, the work that you're describing came from a former PhD / postdoc that I've worked with. Of course, a few other people that I've worked with her. Her name's Antisar Afkaran, and she took the lead on these projects. And she knows my background in phosphorus chemistry and the environment. And so she was kind enough to let me tag along. And I certainly learned a lot about the projects that she was working on and I was partially involved with. Some of the ideas with taking or enhancing nutrient availability in soils, it really surrounds phosphorus in the environment. And there's reasons why, because in soils, phosphorus loves to be loved, meaning it does not like being alone. It wants to be married to something within the soils. And it's rather simple. So at low pH values in soils, phosphorus loves to be loved with iron and aluminum minerals. And at high pH soils, phosphorus loves to be loved with calcium minerals. And so what you find is oftentimes phosphorus, even though there's plenty of total phosphorus in a soil, it's not available to a plant. So we have to almost continuously add phosphorus fertilizers to supply the needs for crops that we grow so we can feed animals and humans. And well, phosphorus is a non-renewable resource, and it depends on what you read as to how long it's going to last. So one of the concepts through Antisar's work and the work that we've published over the last couple of years is really focused on trying to find a way to release or re-release the phosphorus that was applied as a fertilizer to a soil, because we know there's plenty of phosphorus, but it's unavailable. So the approach has been to harness the power of microorganisms that are already present in the soil. And this is a little different than, say, I don't know, like a biostimulant company that creates a specific microorganism to do something, say, on like a seed coating. But the microorganism isn't inherent or indigenous to a soil. So when you enter or you take that microorganism and you apply it to a soil, the indigenous microbial population realizes that there's essentially an invasion and attacks those introduced microorganisms and eventually degrades them. So you don't see this positive response in whatever you're looking for over, say, a long period of time. So the research that Antisar, myself, and others were working on was to look at the microorganism population that's already present in the soil and which microorganisms basically can be flipped on or off depending on whether or not phosphorus is limiting or not. And it's just really exciting work to take a look at the microbial population, say, hey, these are the ones that actually they're amplified. These microorganisms are amplified under low phosphorus conditions to degrade those phosphorus forms that are being loved in the soil and release them back to the plant. It's really cool work.
Yeah, that is really interesting. It's a way to I think there's a lot of like ideas of like inputs, right? How do we input these things into the soil, whether it's fertilizer or the biostimulants, like what you're talking about. And this is kind of why do we need to add things? Well, not why do we need to add things at all, but more of why don't we look at what's there and figure out how we can leverage what's already there? So how have you found ways to try and do that? Or have you yet found any ways to actually encourage the right bacteria?
Yeah, that's a great question. So that's the next step in her research, to be honest with you. She's written 2 papers so far on this subject. And the second paper, which came out in 2024, really focused on those indigenous microorganisms that basically are turned on when phosphorus availability is low to the plant. So these microorganisms can solubilize these insoluble forms of phosphorus in the environment. So the next step would be to see whether or not we can take these microorganisms, which are known, and grow them and then apply them back to a soil. So the soil already knows that these microorganisms are present, but can we increase the amount of these microorganisms that are present to increase phosphorus availability to plants and reduce our reliability on a non-renewable resource?
Yeah, that'd be great.
And I'm glad that she's young, because I'm in the last third of my career, and this is something that I wish I could have done if I was 30, which she probably is 30-ish, She has a lifetime to pull this off. It's going to be really exciting to see what comes of it.
Yeah, and I mean, from a practical standpoint, we probably only have 30 or 40 years to figure it out regardless, where something needs to change in the way we grow our food. That might be rushing things, but I mean, given the fact that we were just talking before we started recording about climate change and the crazy weather patterns that are going on, whatever we can do to reduce petrochemical use is probably going to be a net positive that we very, very desperately need.
Yeah, I agree. That's a good and interesting connection between the fertilizer industry and other means by which we can offset fertilizer inputs, and of course, reducing the impact on the environment.
Yeah, I think it's something crazy. And I know we're talking about phosphorus and not nitrogen, but the amount of energy from the Haber-Bosch process that is used just to create fertilizer is like a not insignificant amount of all of the energy used by humans on the earth. So starting to figure out some of these agricultural components, I think, would be massively significant when it comes to trying to address greenhouse gases and things like that.
Yeah, I agree. The Haber-Bosch process is pretty energy intensive. And it's interesting when you look at other fertilizers, specifically phosphorus fertilizers. that phosphorus fertilizer creation is actually tied into oil and gas industry. Everything is so interconnected. So unweaving this tangled mess of not only just nitrogen, like you mentioned, but phosphorus fertilizers is not trivial.
No, and I mean, something as simple as like plastic, like, oh, we need to reduce our plastic use. Well, it doesn't, in a sense, it doesn't really even matter because it's a byproduct of our oil or petroleum industry. So, like, I know plastic may not exist, but the chemical components that make it up are still being produced in basically our waste. So it solves one problem, but it doesn't really solve the core issue, right? And I think what this is in many ways starting to solve some of those more core issues of how do we fix this thing that's got like an end point, right? A terminal point of like, then there's no more phosphorus. We may not know the day, but we know it there's a finite amount, whether it's 50 years or 100 years or 500. There is a finite amount, and humans will be on the earth theoretically when that moment hits.
Well, yeah, that's true. And I think about this concept with phosphorus because I worked with phosphorus for over 30 years. And when I first started working with phosphorus, I thought about, the non-renewable aspect of phosphorus and phosphorus fertilizers and how can we as humans capture phosphorus in waste streams that otherwise would be like landfilled or just discarded. So that's where I hung my hat for decades. Now this work that we're describing really pivots and talks about microorganisms and the power of microorganisms, something that's microscopic that you can't really see with the naked eye, that's going to do the same, hopefully the same thing as recovering waste phosphorus from sources. The waste phosphorus in this case just so happens to be what we call legacy phosphorus. So phosphorus from continuous inputs from fertilizers that have gone to waste by being loved in the soil.
I love that phrase, being loved in the soil. It definitely like sticks with you. You're like, all right, I got it. I understand it. So that whole side of the research I think is really interesting. Given that it's still in a very early phase, what kind of feedback have you gotten from the industry about like engaging with this kind of concept, like farmers and things like that?
Yeah, it's in such an infancy state that I haven't received any feedback. I don't know if my co-authors have received feedback either, but I would assume once Antisar, if she takes the next step and tries to grow these microorganisms in some kind of media in the laboratory and then applies this on a little bit larger scale, besides like greenhouse trials,
Mm-hmm.
in-field trials, that I think the door might open for her and open for this research. But I have not received any feedback yet.
Okay. When you're talking about this idea of like indigenous microorganisms, the bacteria and specifically, this might be a little bit too granular, but do you have any idea of whether or not that bacteria is actually like indigenous to these regions, or is it just this particular domesticated farm crop bacteria, or is this like ancestral from like pre-agriculture or anything like that? Is there any like context of like, is it going to be, my question really is like, so you found this bacteria, is that going to be the same bacteria on farms that grow the same thing across North America, across the planet? Or is that, again, kind of getting like too granular?
Well, that's a great question. I don't know the answer fully, but when I think about bacteria, there's probably thousands, if not tens of thousands of different genus species
Mm,
combinations that we just aren't aware of that likely do the same or cause the same functions within soils across or within regions or across regions and across the planet globally. So I know this because my wife is a soil microbiologist, so I hear about this often. And
now it makes a lot more sense as you're doing this research.
yeah, I think about what you asked about are the same microorganisms going to be present everywhere, basically? And the answer is likely no, but similar microorganisms will be present everywhere. And everywhere is a really loose term. I should say like places where we grow food. You're likely going to find these microorganisms or similar microorganisms in a lot of different locations.
Yeah, I was just thinking about almost, I kind of always harken back to this like estate, like terroir kind of idea of like how we grow food, how we should think about food systems and things like that, of how the ecosystem can really inform us of what should be growing there, right? And then when you're coming down to this like very simple life form, if that continues to kind of perpetuate that like idea of like how is the landscape informed the way this microorganism even exists on the landscape, and then how has that, I guess, evolved with its use to become, from a prairie to a cornfield or whatever it might be, right? And how that might inform us how we end up growing these bacteria and then putting them into the soil to help unlock the nutrients that we're trying to get out. It offers some really interesting thoughts, I guess, about how we understand and respect the microbiology the way we do, the native trees and native animals and things like that.
Yeah, I fully agree. I think about this topic often, the connectivity and interconnectivity between microorganisms and, say, humans. And I teach this in the class that I teach and I've taught that, when you look at specific aspects of microorganisms and even plants, there is a connection between those two organisms and humans. And so, like, this is a 30,000-foot view, but you probably could take it to the granular level as well. So the 30,000-foot view is, let me give you two examples. One example deals with microorganisms that are responsible for nitrogen fixation in leguminous plants, so alfalfa, soybean, et cetera. And if you look at the chemical or the compound that's necessary for fixing nitrogen, it's called leg hemoglobin, and the structure looks identical to hemoglobin in human blood. They're almost identical, except for one or two elements that are just sort of offset, but they're identical. So you think about the connectivity between humans and microorganisms in that context. We're not even one step removed, basically. The other part, which is really interesting, is when you look at, and I need to pull this up so I don't make a mistake. Give me a second.
Yeah. Take your time.
Where is it? Oh my gosh. I should know this off the top of my head. I've taught this for like forever. What's my problem?
But sometimes it just like slowly disappears because you're not even thinking about it when you're talking about it.
Yeah. Yeah, the connectivity between the leg hemoglobin and hemoglobin in humans, the human microbiology aspect is easy for me to remember because it's just so fascinating. And then the other connectivity is between chlorophyll and, of course, I'm drawing a blank. Maybe we'll just skip that. How's that?
Yeah.
So the second example I wanted to provide you deals with the connectivity between plants and humans. And so when you look at hemoglobin, like I just described, between hemoglobin and these bacteria within plants, there's a similar connectivity. And the connectivity is between hemoglobin and chlorophyll, which is used for photosynthesis.
Mm-hmm.
And chlorophyll actually looks a lot like hemoglobin as well.
Mm.
So there's this interconnectivity between microorganisms and plants and humans with three different compounds that look almost identical, except for the nutrient that's basically stuck holding the compound together. So there's a strong interconnectivity here. And it's, of course, not directly dealing with phosphorus, but there's a connectivity on the micro scale to the plant scale to the human scale that it's hard to ignore.
Yeah, it does feel very much like nested systems. I mean, like from an agricultural standpoint, it's like, well, what's the key compound of like growing stuff and making it bigger? It's nitrogen. But what is nitrogen? It's basically protein. So it's like, you're seeing that same kind of nested system. Like, what is it? Nitrogen is 15% protein, something like that. It speaks to that same point of like, these things are that we think like people eat this and plants eat that. Well, yes, but also like those are kind of stacked on one another.
Well, yeah, they are stacked on one another. And so there's some pseudo redundancy in systems or ecosystems that we may not see. But based on what I've seen over the last or read over the last 30 plus years, we probably can make some pretty good educated guesses or assumptions as to what microorganisms are present across ecosystems globally, and that they're all sort of doing the same thing.
Mm.
And so, yeah, going back to your initial question about this phosphorus solubilizing bacteria, and can we basically raise them, mass produce them, have farmers utilize them so they have less phosphorus inputs from fertilizers on a global scale? I think it actually can happen. I don't think it'll happen anytime soon, but I think it will happen. And, you mentioned phosphorus running out. It's a non-renewable resource on a short-term scale. yeah, if it lasts 200 years or 500 years and humans are still here, which, like you said before, we assume they will be, we better find another way to release phosphorus from the environment besides mining it.
Yeah, or we're in trouble.
Yeah, we're in big trouble.
Yeah. I'll be really interested, I guess. I'm kind of, as much as like it's like you feel like you can learn everything this, or like eventually you're going to be tired of learning stuff, rather. Like I think about, I really kind of wish I could see what things would be like in 500 years in terms of how we grow food, all of the things we haven't thought about, the ramifications of, like, this, for example, if we add bacteria to the soil and we unlock all of this phosphorus, how might that change the way the soil, what a healthy soil is? How do those bacteria co-evolve with these new soils that consistently have unlocked phosphorus in them, and things that may or may not have any significant implications, but like inevitably, if we fundamentally change the way we grow food, which is like the largest use of land in the world, it's going to have unintended consequences. And it doesn't mean they have to be bad. It just means there's things are going to change that we would have never thought of. And then we'll look back and say, huh, obviously that was going to happen. Like, why didn't we think of that? And I'd be really curious to see kind of what those types of things are, if you have any thoughts about that. Just wildly speculate for me.
Yeah, you bring up a good point. I think a lot of people, not a lot of people, but people oversee some of these simplistic views of fixing a problem, like adding solubilizing phosphorus bacteria to a soil to improve phosphorus availability to plants. Sounds like a great idea. It looks great on paper. And then you think about the negative connotations with something like this. I'm going to steer clear of adding a bacteria that is inherently present in a soil, but I want to steer towards increasing phosphorus availability. And I can tell you that we see this all the time globally. When we have too much phosphorus in the environment, it ends up leading to eutrophication of waterways, specifically freshwater. So I'm in Ohio now. One of the biggest issues we have in Ohio is eutrophication of Lake Erie and fish kills and algal blooms and fish kills and degradation of ecosystems. And you could see something like this happening with such a simple concept as increasing phosphorus-solubilizing bacteria in a soil in the future. So hopefully we learn from our mistakes now and we keep these in mind 500 years from now. So it would be really interesting, like you said, to see what would happen. In my case, it would be interesting to see if somebody would cite Antisar's paper from 2023 and 2024 in 2523. So
Yeah, like I said, it'll be really interesting. There have been plenty of papers. Mendel's own work was basically lost until Liberty High Bailey stumbled across it, I think 30 or 40 years later. And, those types of things happen. And now we would like, how did no one see this? But it happens, and then they become important later on. And this could be one of those cases, or it could be something that is fundamental to the way agriculture shifts over the next 100 years. But I don't think it's not significant. There's a lot of opportunity, and I think even with the risks that come with it, it's pointing in a better direction than the way things are going now. And I generally speaking, I call myself a optimistic pessimist, if that makes any sense, where I don't think things are going well, but I think individual things will tend to do pretty well. And I generally believe in the capacity of people to do the right thing when given the full range of options.
yeah, well put.
So in terms of your other research, I know you've been working with phosphorus for a long time. I'm sure you must have some thoughts about how things have changed in terms of research, in terms of utilization, and kind of how do you see things going in the near medium future, given like the rise of, no-till and regenerative agriculture and all these different components that are very clearly advocations for changes that the way we're growing food can't continue. And I think like most people, regardless of politics, regardless of involvement with growing food, I think 90% of people would say there's something wrong with the way we're growing food. Something needs to change. And I think nitrogen gets a lot of the attention, but phosphorus is a pretty big one and pretty fundamental in how we have to address some of these issues. So I'm curious about your kind of like big picture thoughts about how things are moving and if we're going in the right direction.
Yeah, it's a good question. I think I'm also an optimistic pessimist. And so I like to think we're moving in the right direction, although we're moving really slow. I think as a whole, production agriculture is just moving slow in terms of maybe even doing the right thing. Not that people don't want to do the right thing, because it's a challenge to move in a different direction. I work with producers hand in hand all the time, and so I see what they struggle with. They're not rich by any stretch of the imagination for the most part. So to purchase a piece of equipment that would help put them in the right direction is not inconsequential. And what if you had to spend $1 million on equipment just to go to no-till or plant cover crops? You'd go bankrupt. And so it's a challenge, but I think we have a pretty good idea of the direction we need to go based on some tried and true practices that are promoted through the NRCS. But it's just a matter of implementation. And I can tell you, like, if you look back on some of the early works in conservation agriculture, like 50 years ago, maybe longer than that, we sort of knew the direction and we still haven't fully gone in that direction. So it's a little disheartening, but at the same time, there's a lot of people talking about this subject. I've seen it being talked about, regenerative ag, soil health, so much in recent years. It's it is a hot topic that I feel like it won't go away, and it's caught the attention of the public, and it's caught the attention of producers, farmers, at least in the United States. I think they get it. It's just a matter of how do they get from where they are currently economically from point A to point B. That's the challenge.
Now, are you doing any? I know you've been involved with this bacteria phosphorus research. Do you have anything you're studying right now that you're getting ready to release any results on, or that you're excited about working on that you think is going to be important in the development of this kind of research?
Well, yeah, everything.
Staying busy.
Yeah, I'm the kind of person that I, over my career, have focused on a few things, but really, if you look at my publication record, it's sort of broad, although there's some highlights. So phosphorus, certainly biosolids land application, pros and cons, biochar usage in the environment. But then there's all these other projects that I work on. And most recently, I've been focused heavily on soil health, probably the last 10 years. Actually, I've been focused on soil health my whole career. I just didn't know it was soil health. We used to call it environmental soil quality. But I've really pivoted strongly towards soil health, and that's mainly what I focus on. And so what we were just talking about, trying to find, I don't know what you want to call it, the sweet spot in production agricultural systems where you get the highest return in terms of soil health on whatever management practice or practices you're performing, and trying to really tease that out. It's not very easy because, like, here's an example. You might have, like one of the current cases that we're working on, we have 10 different fields that are all really close to one another here in Ohio. They're all managed a little bit differently. Some are managed using conventional farming practices. Some are managed using conservation farming practices. Some are in pasture with or without animals. Some are under forested conditions. You have this landscape mosaic, if you will, like you have many locations. And what does that mean in terms of soil health and maybe ecosystem services? And so currently we're quantifying soil health in these different systems. And so I'll just pick on the agricultural systems. There's 5 or 6 of them. And they're all about the same in terms of soil health, except for the system that's been tilled with conventional tillage practices. But the other systems, they're all about the same in terms of soil health. And so I don't know if this is good or bad. It's good because we don't have just one target. We have multiple targets. Like the bullseye is really, it's bigger than you think.
No.
At least this is what I'm seeing, not just here in Ohio, but I've seen this elsewhere, which is good because that means that it's easier for producers to hit the bullseye. The hard part about this is convincing producers that do or perform different management practices that they basically end up at the same point because they don't think they do. So this is the challenge in my research, is to actually take the research and condense it into a format that is palatable to producers, not only in my regions, but globally.
Yeah. I feel like you're my son does karate, and I feel like you're his teacher who does, after they fight, tells them to close their eyes, and he's going to touch the person's head that won, and he touches both their heads. right? Like you have
Exactly.
to let them all think they won, and they can't know that the other people won too.
That's exactly what this is. That's a great analogy, Andy.
So I do want to shift gears a little bit, talk about some of your work with biosolids and biochar. I've done quite a bit of research on biochar, and it seems like a really great product, but it also seems like one that we don't fully comprehend how to use sometimes. So I'm curious about your thoughts about its actual application in agriculture, like at scale.
Yeah, that's I love this question because I think about the people that I've worked with in agriculture that have used biochar. So I have good friends and great colleagues that I've worked closely hand in hand with over the last probably 15 to 18 years with biochar land application. And I can bet you if I gave you a list of names of these people and you called them and you asked them this exact same question, they would give you the exact same answer. They would tell you that in large scale production agriculture, there is no place for biochar. And there's a good reason for it. It comes down to economics. And so even if you could buy the cheapest biochar you could find on the market, which is probably, let's just I'll take an educated guess here. Let's say $100 a ton. And you needed to apply 5 tons per acre to see hopefully a positive response. So it's $500 an acre. I still work with a producer in Colorado that owns 30,000 acres. So $500 an acre times 30,000 acres is more than his whole net worth. It's a lot of money, right?
Yeah.
So it's what, 15, it must be $15 million, I'm guessing. Nobody's going to do this on a large scale. So I realized this probably after 3 or 4 years of working in land application of biochar in ag settings, ag production settings. Myself and the people I was working with, we pivoted, and a lot of people have pivoted. So our pivot was towards almost niche markets or niche uses. One of the niche uses that we've been using biochar for is sorption of heavy metals in the environment.
Hmm.
So you take biochar and you go to a place that actually can afford biochar. And this could be a place that is maybe owned by, I don't know, like maybe it's a Superfund site that's operated by the US government. So a place that actually puts a lot of dollars into a location to solve a really massive problem like contamination of heavy metals in the environment. So you could take a product like biochar, you have to find the right biochar, but take a biochar that can actually sorb, sequester, and not re-release those heavy metals back to the environment. And so what you can do is take these materials and use them in the field, in place, to solve a problem. So you don't have to scrape and haul and move tons of contaminated material. So we've done this all over the place, and it is a lot of fun. It's not as easy as it looks on paper because not every biochar is the same.
Mm.
So that's one aspect. The other aspect that we're currently working on, and I have no data to share with you, but there's interest in using biochar to remove these persistent chemical compounds from the environment. So chemical compounds like PFASs, these polyfluorinated alkyl substances.
It's a mouthful.
It's a mouthful, but they're persistent in the environment. They don't degrade readily, and they can potentially cause cancer. And they're ubiquitous. I mean, they're everywhere. They're in rainfall, for crying out loud. Oh my gosh. And so can you take biochars to solve a problem? In soils, could you add biochar to sorb, sequester, and prevent movement of these forever chemical compounds into plants that we consume or downward into groundwater that we drink? So that's what we're working on right now. It's really fascinating.
Yeah. I mean, I think I would agree with you. I think that's probably the better usage of biochar. And I know, and I don't know if you can speak to this at all, in some of the research and some of the researchers that I've spoken to that have worked with it, sometimes it doesn't work. And they've struggled to make it work to get it crop improvements, or it's inconsistent in the crop improvements. And it could be just limited data on the soil before they're adding it. But it seems like it's almost a little finicky sometimes. I don't know if you can speak to that at all.
I agree. I think it's finicky. You have one batch of biochar that you take half of it and you put it in one field and half in the other field. You might see two different responses. It's frustrating because you think you know everything and then you know nothing about biochar. So it is. It's really frustrating. Sometimes
It makes me it makes me feel better when you say that and it's not just me.
no, it's not just you. It's definitely there's a number of us that think like this because we've seen it before. It's been a while since I've looked at the biochar literature in terms of positive, negative, or no response. via crops from biochar land application. But there was a point in time, this is probably, I don't know, 8 years ago, the numbers were something, and I'm gonna keep it simple. They were basically split one third, one third, one third. So one third of the time you see a positive, one third of the time you see no, and one third of the time you see a negative response. And yeah, I've seen this before. I've seen no response and I've seen negative response, and it's biochar dependent. Some of the biochars that I've worked with have given those responses because they were wood based, and so there's very little nutritive value in those up front. So I wouldn't have expected to see a positive response, and we didn't.
Mm.
In fact, the negative response was disheartening. We saw a decrease in yield, and if I was a farmer, I'd be a little upset.
Yeah, I spent a lot of money to make less money.
Exactly.
And you've also worked with biosolids a little bit. So I don't know if you can kind of like talk a little bit about what that looks like. I think people have a very specific idea of what biosolids are, but I'm sure it's a lot more complicated.
Yeah, I've worked with biosolids and biosolids land applications since 1991, so I can't get away from it. It's in my blood, not literally, but it's really where I started my career. So biosolids they're a waste product from wastewater treatment facilities. The biosolids that I've used over my career come from all of us eating the food that we consume and going to the bathroom and flushing the toilet. And most people don't think about where it goes because it's gone, but it goes to a wastewater treatment facility that removes biosolids, removes the solid phase, degrades it using microorganisms into a form that is theoretically, well, it's supposed to be reduced in terms of attracting vectors like flies, insects, etc. And it has a high nutritive value. It actually acts almost identical, if not identical, to manure. There's a lot of positives with biosolids. Of course, like with anything, there's negatives. And so I think about some of the positives that I've seen. I've seen improvements in, oh my gosh, improvements in micronutrient concentrations in grains that we raise, to the point where the grains, if you didn't have biosolids land applied, the grain concentrations of micronutrients are below those levels that are considered adequate for human health. So nutrients like iron and zinc specifically, and I think about the plants I'm talking about wheat or wheat grain. In the US, we do a really great job of growing a lot of wheat grain, and we ship a lot of wheat grain to places like Southeast Asia where their diet's almost 40% grain. So it's not varied like we have here in the US. And then they're consuming a product that we raise here and raise here really well, but it's lacking micronutrients. And so that leads to human health issues with malformation of tissue and fingers. And it's painful. And it's painful to watch because we think we're doing a great job, but we're actually doing a disservice for humankind by not biofortifying our foods. And so I've seen this for 30 years where we can biofortify our foods in the field simply by adding biosolids. Now, there are negatives. You can over-apply just like you could over-apply manure. That leads to excess phosphorus in the environment, like we were talking about earlier, and implications for eutrophication. And then by no stretch of the imagination, biosolids actually have some issues with the potential issues with items that we just don't want in there, like plastic, microplastics, whatever else you flush down your toilet, or you're washing your dishes or your clothes that have flame retardant materials in them that are forever chemical compounds that can end up in biosolid as well. So these are the kind of issues that myself and others are studying to see. I hate to use the sweet spot term, but what's the sweet spot? And can we do a better job of cleaning up our waters before they end up in the wastewater treatment facility? So reducing the inputs of these harmful chemicals or potentially harmful chemicals in the product that is a great source of nutrients and a great means by which we can improve human health and animal health by the crops that we raise within these fields. So I could probably go on and on. I'm a strong proponent of biosolids land application for beneficial reuse or beneficial use. But like you said earlier, there's always pros and cons, right? That you pull on or push on one thing in the environment and something else happens. This is what humans do. We're really good at it, which is why I have a job. So, okay.
Yeah, here in the pocket of big soil over there. Yeah, I think biosolids is an interesting concept, and I think utilizing it seems like a no-brainer in a lot of ways. But obviously there's the concerns about like, let's, to the point that you just made, that what is going down the toilet, not just what we flush, but also what's going through our bodies and then down the toilet is a mess. you know you haven't even brought up like pharmaceuticals, like what kind of trace risks are there from that, PFAS, which again, microplastics, all those things that are going through our bodies and coming back out that we're then feeding to plants to go through our bodies. I'd be really interested to see what the long-term risks and ramifications of that are.
Yeah, me too. That's why we're studying it right now. We've got a couple projects funded through government agencies to support this. Just to say, okay, are we seeing no effect, positive effect, negative effect, what have you?
Yeah.
I'll just mention one other thing about biosolids. And I know there's a lot of people that do not like land application of biosolids, and that's fine. But you're going to continue to flush the toilet. Your waste is going to go to a wastewater treatment facility, and something's going to be done with that waste product once it's done. And I can tell you that if it's not land applied, it's going into a landfill. And that might seem attractive to people because it's not going on land, but there's a cost associated with that. And guess where that cost is going to be pushed upon? It's going to be pushed upon the consumer. It's going to be pushed upon all of us. And it's not easy to landfill these materials because they're I don't know how you want to describe them. They call them cake, but they're like brownie mix. They're sort of gelatinous.
Mm-hmm.
And so they don't have a whole lot of strength. And in a landfill, you need strength in order for the landfill to not collapse and spread all over the place. And so if you take all of your biosolids and put them in a landfill, and the landfill has very little strength, guess what's going to happen to the landfill? It may collapse and it
Yeah.
ends where you don't want it to end up. So there's pros and cons to this story, just like every story, like the phosphorus story, the biochar story, biosolid story. It's a real challenge.
Yeah. But I think working with biosolids while also, I think, having your foot in these other areas that are very similar but also very different gives at least your research a really rounded way to access it, that I do think sometimes in our academic structure, how we do research, we see these researchers kind of become siloed, and you almost forget that there's other things going on outside of that bubble, and how your ideas may leak into this or affect, I when I was younger, I was a carpenter, and it was always like, it's the engineer's fault. They don't know how to design buildings because they've never actually like swung a hammer. They never thought about like, okay, when you go replace this, how are you going to access it? All those like very practical applications, right? And I think in academia, the same thing happens both in terms of like taking that research and applying it to actual farming the way you're doing, but also the way carpenters and HVAC guys will see the same problem very differently. That happens in different areas of environmental research. So biosolids versus biochar versus dealing with phosphorus lockup and things like that. But trying to tie all these together, I think, gives a much more nuanced perspective and allows us to better holistically try to address some of these issues in a way that you can get real buy-in from several stakeholders that otherwise is really difficult to do.
Yeah, I agree. I mean, I've certainly seen a good handful of scientists, researchers that have really shoehorned themselves into, I don't know if not really a corner, but they're just this niche. And sometimes they don't see the bigger picture. And I'm certainly the opposite. So I think about what we're doing at the microscopic scale and then whoop, go up to the 30,000 foot view scale and try to apply it across landscapes and everything in between. And that's, I don't know if it's a good or bad thing in terms of a career, but like being a carpenter and building a house, you really know how to build a house. And it would be really cool to go to an architectural firm and learn how to create the drawings and stand and look over somebody's shoulder and say, well, that's not going to work because I can't swing my hammer to put the nail in this one corner. And so if you can piece those two worlds together, like what sounds like you could do, what I've certainly done, you actually have a better understanding of how things work, especially ecosystems or agroecosystems.
Yeah, and I think you're starting to see that with, like regenerative agricultures. Historically speaking, like a very old practice, but in terms of how we're doing it today is a very new practice, right? We're in many ways relearning how to be human with the landscape in terms of, okay, we're doing this regenerative thing, this, high density stock rates. We're mirroring what how like pastoral systems as people used to and still do in places like Africa and Asia, manage livestock, but we're trying to do it without any of that ancestral knowledge, without animals with that ancestral knowledge of knowing how to live on a landscape where they're not fed corn and all these different things that make it so that they don't have to have those instincts the same way we don't. That domestication fundamentally of how we've domesticated ourselves, we've domesticated the landscape in so many different ways, but we're trying to figure a way kind of out of that a little bit. Not to say we need to de-domesticate everything or rewild everything, but rather maybe we went a little too far in one direction. We need to come back a little bit, right? And then like all these different ways of understanding the landscape in different ways that maybe linear science wouldn't have given us an answer for 50 years ago, 100 years ago, that we can now put into greater context.
I agree. I've worked in that realm too. So I've worked in some rotational, actually about 5 or 6 years of my career in rotational grazing or managed intensive grazing. And the idea is to, I guess, pseudo mimic what you would see along or out across the Great Plains or in the plains of the US. And a totally different concept, not easy. It's a high managed system. It takes people keeping a close eye on the system every single day. Like a producer would have a tough time doing some of these things, maybe on a large scale, unless they had a lot of land, and still they would need to manage. But you're right. I mean, we're snapping back, and I like this. This is the optimistic portion of me, like you, right? So we're snapping back. We're going, oh yeah, maybe we went too far. So if we just snap back by thinking about what the system used to look like, and then okay, we have confines, like for example, lots of fences all over the place in the U.S. So how do we snap back without tearing down all these fences? So what else can we do to mimic what the system used to look like that supported animals in the past and make it better in terms of regenerative ag? Less inputs from commercial fertilizers, for example, less runoff, less erosion, less nutrient transport offsite. I mean, all these things that just make a heck of a lot of sense, but it's not easy to fix.
Yeah, I know. I think it was Florida State University released a book, or one of the researchers there released a book. I think it was Florida State, it's down that way, southeast, that was on native forage crops. So like basically using native crops or, perennials, forbs, so on, instead of all these European grasses that we use for livestock, with the idea that it'll be more resilient for the ecosystem. It'll help support the ecosystem more in terms of like specialist species and things like that. As something as simple as how do we make the landscape kind of what it used to be is like still like at its rudimentary state, right? This is like the first book that's ever really addressed it. And that like speaks to the fact that we are relearning kind of how to contextualize the way we do things, the way we grow food. And I think what you're doing is a big piece of that.
Thanks. I don't know that work, but if I had to take a guess, it probably came from the University of Florida, maybe from probably a bunch of researchers. Maria Silveira at the University of Florida. She's into livestock productivity, and she helps run this long-term agroecosystem research network, one of, I think, 18 in the U.S. That's at a university, not the USDA or USDA government site. And she's done quite a bit of that kind of work. It's really, really fascinating, just taking a step back and thinking about what the system used to look like and then trying it to see if it would work.
Yeah, I can grab the book. I can double check it right now if you want to hold 1 second.
Yeah.
It's like right on the other side of me. It's Native Grass Forages for the Eastern U.S. Patrick Kaiser. Of course, it's a
Yeah, maybe she wrote a chapter.
Yeah, she might have. It's out of Auburn University, but...
Yeah, that looks really familiar.
I haven't finished it yet, but it's really good. I definitely think if you're into regenerative ag and native plants and all this fun stuff, I'm sure. I think you can get it for free online too from the University of Tennessee, the publisher. So if you want like a PDF copy.
Remind me the name of the book again.
It's called Native Grass Forages for the Eastern U.S.
Oh, there it is. Great. Thanks. Yep, there it is. The University of Tennessee.
Yeah, I think that's the publisher. not the where it was done. Yeah. So, Jim, I guess let me ask before we wrap up. Do you is there anything in particular that you're excited about that you think you're gonna have some interesting results from, or any research that you're working on, or anything you want to make people aware of?
I don't know if I don't know if I have any results that, I mean, I have a lot of results that are really exciting to me. But I think about what I was a partner in a big program in Colorado before I moved to Ohio that was all focused on soil health. And so here in Ohio, there are a number of people that are trying to push soil health at the state level, including me. So I've tried to roll myself into that group, and I think I've done it successfully to push a soil health bill and to create a soil health task force in the state of Ohio, which actually there's other states in the US. I can't remember if there's 26 or 29 other states that have a soil health bill that's been enacted, but not in Ohio. And I mean, we had one of the almost founding fathers of soil health and regenerative ag right here in Ohio. His name was David Brandt, and he passed away a couple of years ago. It would be great to have a soil health protocol and bill and a task force to help producers, not only in Ohio, of course, this would be Ohio centric, but to broaden it out and be regional centric. That's really what I'm excited about.
Yeah, move it in the right direction. Jim, this has been really fascinating. I appreciate your time. And if you have any new exciting stuff about that bacteria, you have to let me know so we can have you back on the chat about it.
Will do, Andy. Thanks for having me.